Hi everyone, Mr. Boltri here, bringing you video 3.6. We're going to talk about work done by a non-constant or changing force. Now, in order to do so, first, we're going to review the rules for how to find the work with a constant force, and then we're going to expand them to apply to forces that are non-constant or changing as well. So remember, we have these formulas for how to find work. The first most basic is work is energy that's added into or out of the system. So if the energy in the system is changing, then work must have been done. And then we have these formulas: force times the displacement, or force times the cosine of the angle between the force and the displacement times the displacement. And that's if the force is not in the same direction as the displacement. This is if they are both in the same direction, because the cosine of 0 is just 1. So that's the force times 1 times the displacement. And then if they're vectors, then we can do the dot product or the scalar product. So these are all of our formulas that we've been using so far. And I'm not really going to change these formulas at all because I've already shown you the advanced formula in terms of taking the integral. But let me just take a step back. And when we look at the work done by this constant force, we took the integral over the displacement of the force. And we said the work, because they're in the same direction, we would have to have been told that in the problem. So then it's just what this is just force times the displacement, because the area of a rectangle is just length times width. And up until this point, a lot of the problems have just been take the force, multiply it by the displacement. If you're given a word problem, there might be an angle between them, so you need to include the cosine theta, but it's just taking the two and multiplying them by each other. And the reason that works is because we're finding the area of this rectangle, and the area of a rectangle is just length times width. So we can just take the two things and multiply them by each other. So I just kind of wanted to show you that when we take the area, when we integrate this force displacement graph, it is literally just the rectangle length times width. And that's how the formula is just so easy. We just multiply them by each other. So I'm not really going to change the idea of us taking the area of the force with respect to the displacement, but the shapes are going to be more complicated. They're not going to be nice length times width rectangles. So for example, in this situation, the force of the spring is not constant. As you're pulling on it, doing work to it, adding energy to the system, you're changing the elastic potential energy as you pull on it, thereby doing work on the system. And the force that you're needing to pull with is greater and greater and greater as you pull more, because the spring is getting more and more stretched, and so it's pulling back more and more. So if you wanted to look at the work done, it's still the same rules. Again, assuming it's in the same direction, we can multiply by the cosine of the angle 0, and it's just 1, but I should probably be including those cosines of 0 in there just so it looks like I know what I'm talking about. And you'll notice that the area now is not just a length times width, because if we were multiplied by the force, if we were multiplied by 9 newtons times 3 meters, we would get the wrong work done by me pulling on this spring. It's not 9 times 3, it's 1/2 times base times height. It's 1/2 times 9 times 3, which feeds right into our elastic potential energy formula, which is 1/2 times the force times the stretch, or 1/2 K times the stretch squared. So that is, again, we are, for this work done by a changing force, we are still just integrating the force with respect to the stretch. But now it's not a nice length times width rectangle, it's just a triangle, 1/2 base times height. So that is an easy shape for us to find. And before I move on, let me just briefly touch on kind of an interesting relationship here. So if the force is increasing linearly, and we were to integrate, let's say between 0 and 1/2, 1/2 and 1, 1 to 1/2, if we were to sort of keep making our triangle bigger and bigger and bigger, what would the elastic potential energy graph look like? So it would look like this quadratic, because the linear increase, and we find progressively larger areas, is going to give us a one order magnitude higher function for the elastic potential energy. And that follows our power rule for integration. When we're taking the derivative, the power goes down 1. When we're taking the antiderivative or integrating, the power goes up by 1. So a first order function becomes a second order function. But the interesting thing that I wanted to point out here, which we'll talk more about in our next video, is that if integrating the force of the spring gives us the change in elastic potential energy, then the opposite should be true. Taking the derivative of the elastic potential energy should give us the force of the spring at that point. So remember, taking the derivative is finding the slope of the tangent line. So if I were to find the slope of the tangent line, let's say at a stretch of 2 meters, hopefully it would give me the force of the spring at 2 meters. And so we'll talk more about this in the next video, but I kind of wanted you to start to put together the relationship between the antiderivative and the derivative. If you can take the antiderivative of something and find the work, the change in energy, then you should be able to take the derivative of the energy and find the force that is doing that work. But so now just to sort of wrap everything up is, so what if we have a weird shape that we can't find the area of? So we know rectangles are length times width. We know that triangles are 1/2 base times height. But what about this area? We sort of don't have a formula for how to find the area bounded between the horizontal axis and this curvy function. So what we can do is, well, we can approximate the area by, I don't know, let's just let's approximate the area using rectangles. So I'm going to use a left Riemann sum between 0 and 2, 2 and 4, and 4 and 6. And so I get this area, which is not the best approximation, but it's not the worst approximation either. And then what can I do to make that approximation a little bit better? Well, maybe instead of having rectangles with a length of, or with a width of 2, I can do rectangles with a width of 1. And we can see that's starting to look quite a bit more like the shape. And then I could do rectangles with a width of 1/2, and it's starting to look even closer. So I could do a width of 1/4 or 1/8 or 1/16. So I really want to make that width as small as possible, and then it's going to be really close to the area of the region between the function and the horizontal axis. But I don't want something that's really close. I want something that's identical. So then we're just going to, instead of making the width of the rectangle really small, like 0.01, let's make the width of the rectangle infinitely small. Let's find the limit as the width of that rectangle goes to 0, an infinitely small rectangle, and then a whole bunch of maybe an infinite amount of infinitely small rectangles, and that's integration. So that's the left Riemann sum, and then the limit as the width of those approach 0. And so now we're talking fundamental theorem of calculus stuff, which you guys either are learning or will learn very soon. But that is, I just wanted to remind you that that is just taking the integral or the antiderivative from 0 to 6 is going to give us the exact area of this shape. So just a quick little reminder, it might have been a minute or two since we've done the antiderivatives, integrals. Remember, we have the power rule for antiderivatives, which, remember, the power rule is the opposite of, so when we were taking the derivative, we took the power down and then decreased it by 1. And so now what we're going to do is we're going to increase the power by 1 and then divide that by the front. So remember this example from way long ago, video 1.6. And just I need to remind you of the power rule for antiderivatives. And then also, if we're looking for the area, then we're going to be talking about the definite integral. So this is the definite integral of velocity with respect to time, which, remember, gives us displacement from 0 seconds to 5 seconds. So that's what the 0 to 5 means. And then remember, with an antiderivative, we always want to have the plus c. But with a definite integral, you don't need the plus c because you can just choose it to be 0, because when you subtract it out, it doesn't matter what you choose for the plus c, it's going to be 0. But if this is a indefinite integral, so we don't have these endpoints, then we either have to write plus c, or in physics, more often than just writing plus c, we're often going to have to solve for the plus c. But like I said, if it's a definite integral, you can just choose 0 because it's going to, no matter what you choose, it's going to subtract out, because you're going to have plus c here and then minus plus c here, and it's going to be 0, or it's going to cancel out. So we find the value, we plug in 5 for our antiderivative and then 0 for our antiderivative, and subtract them by each other, and then get the total area of this region. So that's just a quick reminder of how to do integrals and how to do definite integrals and indefinite integrals. And we're going to do some practice problems with some non-constant force and other applications of calculus in our next class. But until then, this is Mr. Boltri wrapping up video 3.6 on the work done by non-constant forces, and go Bears.